Hey everybody. So this video is going to be about something we're going to call the normal distribution. So I want to start just by looking at some histograms of several different things, and really what they're of is fairly unimportant to me for this video, though they are interesting in and of themselves. I do want us to notice, though, that what we're looking at here, these histograms, this one on the upper left is birth weights in pounds. We've got one of height in centimeters and kilograms of weight from a class at UC Davis. We've got some birth gestation periods and temperatures. So people did studies. They collected, anywhere from 1,000 for this one. These other ones had a couple hundred data points, and just made these histograms, right? Well, these are, first of all continuous data, right? Weight, height, time. And we also notice that while they're not perfect, they all seem to have some characteristic shape in common, right? Some more so than others. Right? But it's something you've probably seen before, sometimes called a normal curve or a bell-shaped curve, right? Again, they're not perfect, but the general characteristic is, if we were to compute the mean of these data, right? The mean for this data is somewhere in here. Most of the data is near that mean, right? With very little of it in the outside, right? Very little of it out at the outskirts. Okay, and this is the kind of data we're talking about, things that fall into this general pattern that we will be calling the normal distribution. Okay, so that's the distribution we're talking about now. It is one of the most, if not the most, important distributions there is. It is one of the most important distributions. It is what's going to define most of what we talk about. Somehow it's going to impact almost everything we do for the rest of these videos moving forward for a while. It shows up all over the place, right? So these examples here, if we were to do a study of the wing length of some kind of insect, we would often find a normal distribution, or the lung capacity in some kind of animal, we would often find a normal distribution. So there's lots and lots of things that this normal distribution shows up. So let's talk in some detail about the normal distribution. So let's say, so the normal distribution, we'll start with a random variable. So I'm going to call it X. Is a continuous random variable, right? If it follows the normal distribution, right, meaning it has that typical shape that we saw, the distribution is in this characteristic bell shape, right? This, remember, is going to be our probability density function, right? The same kind of thing we saw in the previous video about the uniform distribution, where we use this density function and we find areas underneath it to represent probabilities between two data values, right? So in this case, I'm writing down a picture of what this area would represent the probability of our variable being between these two data values. We get that from the area, which we'll talk about how to find those areas a little later. But our notation will be that X follows, we use an N to represent the normal distribution. And we write, so remember in our previous distributions, the binomial, we needed two things. We needed to know the number of trials and the probability of success. For the Poisson distribution, we needed to know the average over the interval. For the uniform distribution, we needed to know where it began and where it ended. Well, it turns out that there are two pieces of information we need to know about a normal distribution in order to know everything we need to know about it. And the two pieces of information are the mean and the standard deviation, right? So this is our mean. This is our standard deviation, right? If we have those two pieces of information, we can, in theory, draw this curve perfectly. In reality, we would use computer systems to do it. And from that information, we can also compute all of the areas having to do with this random variable, okay? Let's take a look at this with a little bit better drawing than my little sketch. Let's take a look at, where are you? Here is a picture of, let me remove these. Here is a picture of a normal curve, right? We'll get into that shading in just a moment. But what I want us to notice right now, I'm gonna change two things about it. Remember I said there are two things we need to know, the mean and the standard deviation. So I'm gonna start by changing the mean of this normal distribution. And notice what it does is it changes the location of the curve. The mean is always going to be located at the peak of this curve, right? So if I put in a line, right, that vertical line that I've just added to this graph is at the mean as I'm changing it, and it always coincides with the peak of the curve. So the mean changes the location. The standard deviation, remember, is a measure of how spread out data is. Well, changing the standard deviation changes how spread out the curve is. It's still a bell shape, but we can flatten it, or we can give it a sharper peak by making it a smaller standard deviation, right? So with those two pieces of information, we get to understand everything about this curve, at least all the stuff relevant to us. And so if we were, for instance, looking for the area under the curve, right, depending on the standard deviation, right, depending on the shape of this curve, we will be able to compute that, that area, right? And so that's the goal of these kinds of problems. So let's do an example and see how we can compute these things. So let's look at a different picture. Here I have I have the normal distribution for a particular situation. So let's say I have a random variable, I'll call it x, which is going to be equal to birth weight. So I'm imagining there's some population of people, maybe it's some particular nation or community. There's a birth weight in, what was this in ounces, I believe. Birth weight in ounces. And let's say this is known to follow a normal distribution with a mean of 100 and a standard deviation of 6. Okay, so that's our situation, and this is a picture of it. Notice that this graph has its peak, right? Here's 100 down here, and we see the peak right above it. The standard deviation decided how pointed this was. I want to ask some probability questions about this distribution. I'm going to ask 3 of them. I want to ask, what is the probability that a baby is born and its birth weight is above 116 ounces? Let's ask the probability that a baby is born and its birth weight is below 89 ounces. And let's ask the probability that its birth weight is between 89 and 116. So I want to answer these 3 questions. That's the goal of what we're doing right now. Let's have a picture of these first, though. So above 116 ounces, what that means we're trying to compute, it's pretty small, but you'll notice down in the lower right of this curve, there's a purple shaded area that I'm turning off and on right now. That's the area above 116, and that's what represents this probability. right? That area is this probability. Whatever we compute this area to be, some number between 0 and 1, that's going to be the probability of being greater than 116. Then we can look at this blue area is the area below 89. And that's going to give us the probability for the birth weight being less than 89. And then finally, this orange area represents the probability of being between, right? So one thing we should notice is between these three areas, we are covering all the area under this curve, which means that this total area, in other words, these three probabilities should sum to 1, right? It's just like adding up all the probabilities in a probability distribution function given as a table. We've done those before where you add up the 3 or 4 or 10 values and they add up to 1. Now I'm looking at all the areas together, which represents all the probability. It has to sum to 1. In other words, it's saying what's the probability that the baby is born and it has a birth weight, regardless of what it is, right? It's going to have a birth weight. So let's see how we compute these. Well, the good news, perhaps the good news, depending on how you think about it, is we don't have to work very hard. If you really wanted to, you could answer these questions using some calculus. Moving these over here so we can see the screen. But we're not going to compute them that way. We're going to use a little normal distribution calculator. So this is one I go to often on this online stat book. It was the first result in Google years ago when I started doing this, and I've been using it ever since. So it gives you a picture of a normal curve. This one has a mean of 0 and a standard deviation of 1. But that's not the normal curve we care about. Ours has a mean of 100 and a standard deviation of 6. So I can put mean of 100, standard deviation of 6. Notice it changed the scale at the bottom, even though the shape didn't change. We're going to ask the probability that x is above some number. So notice it has above here, and I've got to give it the number that I want. I want to know the probability that we're above 116. And notice how the picture has changed. Now this little grayed area, right, we can barely see this little area down here. That is the probability that x is greater than 116, right? And then our answer shows up here. And that is all we need to do, right? That is all. We're not doing these probabilities with calculus, which would take a whole big long process. We just need to understand what these answers mean. I want to make sure we understand it's connected to this graph through this picture, because as we'll see later on when we do more complicated problems, understanding the picture is going to be very important for us. And we got to understand what this number means. This number is telling me the likelihood, the probability, excuse me, that a baby is born in this population with a birth weight above 116 ounces. Okay, let's do the other questions. Our mean and standard deviation are already in there. We can compute below 89 in a similar way. And we get 0.0334. Let's put that in here, 0.0334, right? A slightly, a bigger probability, almost 10 times bigger, and we can see that in the picture. This is a much bigger shaded area. All right, and then we can do one more. We want to do the probability of being between 89 and 116. So let's do that. 9, 6, click this. And we see this huge shaded area, much bigger than the other two, and a much bigger probability. Right now our probability is above 96%, or 0.9628. Okay, and if you want to, let's just do it for once. 0038, 0.0334, 0.9628. Let's add these up. 12 gives me, oops, sorry, that's supposed to be a 0, carry a 2, and I get 6, 8, 10, carry a 1. 10 carry a 1, and I get 1.000, right? So even if that had worked out to 0.999, I would have been satisfied. Sometimes because of rounding, these most likely go on forever. But we expected the answer to sum to 1 because these cover the entire sample space, right? Remember, this horizontal axis is the data values, and we looked at the probability of being above 116, below 89, and also in between those two, and that's all the possibilities there are. Remember, I didn't put these in, but when we talk about these continuous distributions, putting in the equal to or not doesn't change anything. So maybe I should write it this way to really emphasize that we're now including every single value, and we get a probability of 1. Okay, and that's it. That's all we have to do in order to compute these probabilities, and we'll always have, as far as I'm concerned, access to this or some similar kind of probability calculator. Okay, let's ask one more question though now, a different type of question to go in the other direction. Right now I gave a weight and I wanted to know a probability. Let's ask a slightly different question, or maybe a significantly different question, depending on how you think about it. What if I instead wanted to know, so let me get rid of some of this. Maybe I can just, yeah, let's get rid of all of this, or at least put it off to the side. Oops, that's interesting. All right, let's put this over here. Let's now ask the question, what is the 90th percentile? Okay. So first we have to remember what the 90th percentile means. That means it's the data value. That, in our case, that means a birth weight above or equal to 90% of all data, right? Of all birth weights, right? So in other words, if a baby is born, we want to know what weight would that baby be in order to be above or equal to all the other birth weights, okay? What that really means is we're looking for the value so that being at or below that value is a 90% probability, right? 9 times out of 10, babies will be at or below that value. So that means that weight is at or above 90% of all values. In other words, we're going to say we want to know the probability that X is less than or equal to some weight should be equal to 0.90. That's the number we're looking for, okay, right? So this calculator we have here won't do it for us. What we have instead is an inverse calculator. It just means we're going in the other direction. And it's just as simple to use this. I need to tell the computer what normal distribution I have. It's the one with the mean of 100 and a standard deviation of 6. And I need to tell it what area I'm covering. And I want the area below this, right? So before we compute the answer, well, the answer I guess is there, but let's talk about it in detail. Right? We were looking for some weight below which that a baby born being at or below that weight was 90%, right? This is our picture. There's 90%, or 0.9 is the area of this whole shape below. And what this thing has calculated for us is that this value is 107, let's just call it 0.7 ounces, right? In other words, the probability that X is less than or equal to 107.7 ounces is equal to 0.90, right? So it's just the reverse of the process we just did. So the answer to this question is 107.7 is the 90th percentile. Okay. Again, we computed this using an inverse normal distribution calculator, right? Again, I just typed in those words into Google and found this from the same people, this online stats book. the important thing is understanding, knowing what they're telling us so that you can interpret a question and know which piece of technology you need to turn to. Okay, so that's it for our introduction to the normal distribution. We've got a lot more to do. I'm going to do it in other videos. We can kind of chunk this out nicely because they're going to get unbelievably long if not. But that's it for now. Thanks, everybody. And I will see you next time.